Welcome everybody to the webinar of today. The speaker of today is Caroline Nore, and she will talk about flows in liquid metal batteries. So as usual, I introduce the speaker very briefly, and then I leave her the floor. So Dr. Nore has been a fellow of École Normale Supérieure de Lyon from 1988 to 1992. And during this time, she obtained a Master of Science in Statistical Physics and Nonlinear Phenomena from the same institution in 1990, as well as a Création in 1991. In 1995, she obtained her PhD in fluid mechanics from Paris 7th University, Paris Diderot, and her habilitation in physics from the Paris Sud Université in Orsay in 2003. Dr. Nore has held various academic positions. She started her academic career as a teacher assistant at École Normale Supérieure in Paris from 1993 to 96. From 96 to 2007, she held the position of assistant professor at the University of Paris Sud in Orsay, and from 2000 to 2002, she was a CNRS research scientist at LIMSI. Since 2007, she has been a professor at the University of Paris-Saclay in Orsay, and her research interests include magnetohydrodynamics, turbulence, liquid metal batteries, instabilities, and high-performance computing. So it's with great pleasure that we have here today Caroline Nore. So Caroline, I stop sharing my screen. And
yes.
If you want, of course.
So do you see my screen?
Yes.
Yeah. Do you see my screen?
Yes. Yes.
Yes.
Yeah.
Good. So thank you for the. Can I start? Yes. So thank you for the introduction and thank you for the invitation also. So today I will present our results about flows in liquid metal batteries, and these studies were made in collaboration with a lot of people. But my main collaborators are indicated in bold. So Wietze Herreman from FAST now, Sabrina Bénard defending her thesis in November 2023. And Loic Cappanera is on a tenure track in Houston University, and Jean-Luc Guermond is a professor of applied math at Texas A&M. And I have all the other colleagues here from Germany. All right, so we are interested in flows in liquid metal batteries because we all know that the challenges for renewable energies coming from wind or sun is that there exists an offset between the peak supply of these kind of energies and the peak energy demand, as it is shown here. During the time of the day, you have the supply during the day, but the demand is mainly in the evening. And so we need, in fact, to have a solution and to have a static storage at a large scale. And so a proposition is to use liquid metal batteries. And for that, I will follow this outline just to explain you what is exactly a liquid metal battery that I will call LMB here. And because I like fluid mechanics, I will focus on the flows. And I will show you that we had two different points of view before 2018 and then after 2018. And we start, in fact, these kind of studies around 2013. And I will mainly focus on two different flows, the metal parallel instability, I will explain you, and another flow which is not coming from an instability, which is called electrovortex flow. And then I will conclude and present some perspectives. So first of all, what is a liquid metal battery? So a liquid metal battery is a superposition of three liquid layers at high temperature, usually above 350 degrees Celsius, because you use metal and you need to have this the temperature above the melting point of all the metals included. And so, for example, here is a scheme of a discharge of the liquid metal battery. So you have the three different liquids, pure liquid named A, it is light, and there is a dense liquid at the bottom, which will be a load, and it is heavy, and in between you have a molten salt. And during discharge, you have a reaction, an electrochemistry reaction, during which the atom A will form an ion, and this ion need to go through the molten salt, and it will be alloy at the bottom layer, and you get light on your bulb. And during charge, you get the opposite, reaction, for which this time the ion will go from the bottom part, the bottom layer, through the molten salt, and will will accept an electron here, and will recover a pure A metal. And so you see that electrochemical energy is converted into electrical energy and vice versa during charge. And so what are the advantages of this liquid metal battery with respect to usual lithium-ion battery? So in fact, I've compared the two technologies here, but I will mainly focus on the advantages of the liquid metal battery that people want to manufacture, and at the end you will see that you have some realization. Sorry. Oh. So first of all, one advantage is that people want to get cheap liquid metal battery using cheap pairs of liquid metal at the top and the bottom. And also, the voltage is quite okay. It's less than the lithium-ion battery, but it's kind of okay. But one of the main advantages is that you can't have interface degradation, because interfaces are not between solid and liquids, but they are all liquids. And so you have, therefore, you have less interface degradation, and so the lifetime of the battery is therefore increased. And so we have different realization. They appear, in fact, in the 1960s, but after they get into light again, thanks to the professor Donald Sadoway from MIT, and they made a lot of different realization using different light metal like lithium or magnesium, and they use adapted molten salt in between. And here you get the alloy, which can be bismuth or antimony or lead or whatever. So here you see, for example, that there is a small liquid metal battery made with magnesium and antimony that I will be using for most of my numerical simulations. And so the advantages is that they are simple to assemble because you only use the fact that they have different density. And so it's only stratification due to the gravity. The aim is to use materials that are low cost and that are abundant on Earth. You will have a long cycle of life, and you can scale this battery quite easily because you just have to increase, in fact, the container. But they also have some disadvantages because you need to heat all these metals, so you have high operating temperature. The voltage around 1 volt is quite small, and it is also sensitive to motion because it is all liquids. And so, of course, you cannot use this kind of battery in a car. It's not possible. It's only for having a static storage. All right, and so we have flows in between these 3 layers of liquids. And so these flows can have some advantage, for example, because during the transport of, for example, this ion of lithium, we have mass transport, and if you have too many ions of lithium going there, therefore you can see that there will appear a solid alloy, which is called an intermetallic. And what you want is you want to have flows in the alloy in order to avoid this kind of intermetallic. So the flow can be advantageous, but they can also be dangerous because you can get also a contact between the bottom layer and the top layer. And so in this case, you will have a short circuit. All right. So therefore, we have this kind of different flows. So the intermetallic layer with mass transport, and we have also the danger of electrolyte rupture. And so before 2018, we were mainly considering that flows are kind of dangerous, and we wanted to have some scaling which can tell us how to avoid short circuits. So we wanted that the flow are not too intense. But after we change of paradigm, saying that in fact, because this there is some mass transfer between the top layer and the bottom layer, we need in fact to have an alloy which is as homogeneous as possible. And so the idea is to use the flows to mix the alloy. So we have change of point of view. But before, we need to know how to which kind of source of motions you can get. In fact, you have electric currents through this battery, and you also have induced or imposed magnetic field. So therefore, you will have a Lorentz force, and so you have force which will in fact create some flows. And so, for example, we have studied Taylor instability, metal pile roll instability, and electrovortex flow. But you also have compositional gradients because you will have some ions coming from the top to the bottom layers. And so you can get also solitary convection. And you can also have thermal gradients because here in the middle, you have a salt, which is an electrolyte and which is very bad conductor, 10⁴ less conductive than the liquid metals. And so therefore you will have Joule effects, which is localized inside the battery. And so you have a thermal, as if you have a thermal resistance in the middle, right? And so in fact, we didn't study these thermal problems. We studied these instability, and I will today focus only on the metal pile roll instability and the electrovortex flow. All right. And so for that, what we have done is that we have conducted theoretical studies, but also numerical studies using the multiphase SFEMaNS code that was developed during Loic Cappanera PhD. And then what we have is that we have the Navier-Stokes equations as usual, where Ui are the velocity in the layer I, the density rho I which is the density of the layer I, and you also have the Lorentz force here, for which you have the density current J cross the magnetic field B. And all these fluids are incompressible. And here you have the magnetic induction equation. And the two coupling terms are the Lorentz force in the Navier-Stokes equation, which make the flow, which can drive the flow. And you have also an interaction between the velocity and the magnetic field from the Ohm's law. And all these equations are called the full magnetohydrodynamics equation. But sometimes, because the magnetic Reynolds number, which is a non-dimensionalized parameter, which is important in this kind of liquid metal, is very small because you have the magnetic permeability of the vacuum, which is small, the electrical conductivity, which is large, but in fact, this product is around 1. And so you see that after you have the characteristic velocity and the characteristic length, and all that is quite small for this liquid metal, And so therefore, sometimes you can use some simplified model for the magnetic parts, for which you have the current density, which will be given by this formula with phi, which is electrical potential. And we need that the divergence of J is equal to 0, that is a conservation of the charge. And we have this Ampere law. And that is what we call the quasi-static, or even you can use static MHD when you don't have this term here. And you have also to add the equation for concentration if you want to model that, or the equation for temperature, etc. And for performing this numerical simulation, we are using our code that we have been developed for a long time, since 2001. So mainly we use axisymmetric domains. And so we use cylindrical coordinates with R the radius, theta the azimuthal angle, and Z, which is the vertical coordinate. And in theta, we will use Fourier transform in cosine and sine. And in the meridian plane, we will use finite element in R and Z. And so here, for example, I'm showing a meridian plane in R and Z, and you can see here the kind of grid I'm using, which is built with some triangle, and this code is massively parallel. All right, and so I will be using usually M as being the number, the number for the azimuthal mode, right? All right, so let's start with metal pad roll instability. So it is an instability, so you need to know what is the basic state. And so the basic state, in fact, is represented here when you have 2 layers, and here when you have 3 layers. And so you will consider an homogeneous current, which is given by the density current J here, and you have an external magnetic field. Usually it is vertical. It will be due to the external electrical circuit, I will show you. And so in fact, this mechanism is well known in aluminum reduction cell with 2 layers. And people have studied that for a long time, because we know that it can lead to very dangerous short circuit if this instability starts. And so the mechanism is I will show you is due to CLA, and it is the best known. And for example, I show you, for example, a lot of different, a typical aluminum production facility with a lot of all Héroux cells, which are all connected in series. And so here you have only one in green. So it's about 10 meters here, 4 meters here, and about 1 meter height. And so you have a very large current, very intense current coming from the center line. And then here it is injecting at the top of the cell. And then you will add the current returns from below. And then the current will go towards the next cell, which is connected in series. And so all that will be connected. And due to the fact that you have a circuit, you will have a magnetic field, a background magnetic field, magnetic field which is vertical mainly. And so all that will in fact create this metal pad roll instability. So let's look at the mechanism in cartoon. So here is only one all Héroux cell. You have the carbon anodes here, which the current is really very intense, like 400 kiloamps going from top to bottom. You have a bad conductor here, which is a mixture between chloride and alumina. And at the bottom, you have aluminum, which is a good conductor. All right, and you see that it is a rectangular cell. Okay, so now, and we know that due to the external circuit, you have an external magnetic field, a perturbative one. And so what you start to understand that is that you have an equilibrium cell with no flow and a flat interface with this big J, which is a perfectly homogeneous current density going from the top to the bottom. And so now imagine that you have a small perturbation. So therefore, you have a slope here. And because in yellow, you have a very bad conductor, in fact, the current will redistribute such that it will go mainly through the smallest part, the thinnest part here, in order to have less ohmic, to encounter less ohmic resistance. And so therefore, the total current will be this basic current plus a small perturbative current that I call the current excess due to the wave, and it will follow this path, in fact. And so you see that it will be mainly horizontal in the aluminum here. And so now we know that we have a vertical magnetic field. And so J cross B will give you the Lorentz force. And so you see that J cross B will push, in fact, the fluid here, the bottom fluid from the front part to the bottom part of the cell. And so you see that you will have, therefore, the thinnest part will be at the back part, and therefore the phenomena, everything repeats. You have this excess current here interacting with the magnetic field. The Lorentz force push the fluids, and so on. And so in this way, with the J going from top to bottom and this BZ, which is from bottom to top, you get an anti-clockwise wave. And because we have also a good conductor at the bottom and a bad conductor at the top, these signs are kind of important. I will just summarize here. So you have an anti-clockwise rotating wave if you have this product with the current density with the vertical magnetic field smaller than 0, and you have a bad conductor above a good conductor. And same if you change all sign. and you will have a clockwise rotation wave in the opposite case. So anyway, these kind of waves are called, in fact, gravity waves that are excited due to this magnetic field, which is outside the external magnetic field. And there is an instability criterion, which is due to CLE, which tells you that if the product of if the Lorentz force divided by the, let's say, the gravity potential force is greater than the threshold, therefore you have an instability. All right, and so what people just use this kind of instability in the liquid metal battery context, starting with Zikhanov, and a lot of people followed, including us. So what we have done is we are focused on a cylinder because we want to have axisymmetric geometry, and we have performed some linear stability analysis. So using M=1 mode, because it is the most unstable mode. And so we will focus on the growth rate lambda. And so we have developed a theory which is for cylinder with arbitrary fluids and any depth, including dissipation due to the viscosity and to the the Joule effect, in fact. And so here lambda v can be or positive or negative, but although the two terms here, they comes from dissipation, so they are negative. All right, so that is the main result, was to be able to get these terms here. And so we have in fact validated the viscous damping with respect to experimental results. We have validated the magnetic damping numerically. And we have used two codes, our codes and our German colleagues use the OpenFOAM code. And why? Because it is a quite difficult benchmark. And what I'm showing here is the growth rate in 1 second as a function of the current density here. And so in the theory is presented as dotted line, and the different two codes, the result of the two codes are here. And we can say that there is a good comparison between the numerics and the theory. And so now let's look at the results. So here you at the top you have the cryolite plus the alumina. At the bottom you have the aluminium. And so in this case, what we have is that we have J multiplied by BZ, which is positive, and we have a good conductor at the bottom and a bad conductor at the top. And so therefore we are supposed to get clockwise wave. So starting from a small perturbation, here I'm showing the interface, and you see that after a while you have this sloshing motion, which is clockwise as expected. All right, and so thanks to the theory developed by mainly Wietze Herreman, we were able to get all the growth rate for any conductors. And people thought before that you could get this instability only with bad conductor and a good conductor. But in fact, with the theory, we can use two good conductors, and we have tested with an experiment, with a numerical experiment, I can say. If we take gallium above mercury and realistic density and realistic vertical magnetic field, and so we have redone this. We have redone the kind of computation I've shown you, but it was really challenging, even in a small cylindrical cell. So here the diameter is 4 centimeters, the height is 4 centimeters, and you take gallium and you take mercury, you take the real parameters, and I will show you that we get some velocity which is around 8 centimeters per second. And so that tells you that the Reynolds number is about 14,000, okay, with DNS. And so here, for example, in this case, GBZ is positive, but bad conductor is at the bottom. Mercury is less conducting than the gallium. And so therefore we will have anti-clockwise. So the interesting things here is that we see in this slice, we see in fact the amplitude of the velocity. And you see that it is quite high, 8 centimeters per second, and you can get a lot of small scales. So it's kind of turbulent motion, especially in the top layer. Right. So this difficult theoretical computation could, in fact, led us to propose some experiments that are quite original, and so we have proposed some more details in this paper here. But the thing is that we can ask ourselves, do we have this kind of instability with 3 layers now? Because we will have a good conductor at the bottom, a good conductor at the bottom, good conductor at the top, and a bad conductor in the middle. All right. So we have done this kind of study with our colleague from Germany using OpenFOAM, and in this case we have used the liquid metal battery made of magnesium at the top, magnesium at the top and antimony at the bottom. But the antimony is too heavy to move, and so you have the 2 interfaces which are shown here. I'm showing in the slice, I'm showing the amplitude of the velocity, and with I'm showing as streamlines, in fact, the current, the perturbative current, the excess current, and so you see that it forms some loops inside the fluid. And so if I will show you here a movie, and so even if it is a 3-layer system with 2 interfaces, we see here that the antimony is too heavy to move. So in fact, this system just like as a 2-layer system for which you have the sloshing motion only of the interface of the top interface. Okay, so the idea after was to in fact to generalize to 3 layers using linear stability analysis with Bessel function, but now we have 2 differences in density between the different layers, and so we can have different phenomena. So, for example, here, if the bottom layer is too heavy, therefore the interface won't move, and therefore you can get only one moving sloshing interface at the top. That is what we have. We have here for the magnesium antimony liquid metal battery, and here what is shown here is the theory for the 3 layers compared to the numerics. So we have quite a good agreement. But now imagine that these 2 differences in density are of the same order. So therefore you will have 2 possibilities between the 2 interfaces, or they can be coupled together in a symmetric mode, and that would correspond to a fast wave, or they can be coupled with an antisymmetric mode, meaning that they will slosh, but antisymmetrically, if I can say. All right. And so what we have done is that we have performed some simulation in 3 layers. And so here what is plotted is the period of this sloshing motion with respect to the ratio between the difference between the density. So the density between ρ2 minus ρ1 divided by ρ3 minus ρ2 here. And so what we see here is that in square you have the simulations. So there are a good agreement between the theory in solid line and the simulations, the direct simulations. And also what we see is that we need that this ratio is around 1 in order to have the 2 interfaces move symmetrically, while when this ratio is different from 1 or smaller or greater, you get the antisymmetric mode. All right, so there was a good agreement for the period of these sloshing waves, and we have compared also what is the threshold with respect to the current density as a function of this ratio of the difference of on the densities. And so here we see that numerically we obtain the slow wave, meaning the antisymmetric mode in this part and in this part, while in the middle we get, when the ratio is near 1, we get the symmetric mode. But in fact, this symmetric mode was not obtained as linearly, but we needed to integrate for a long time, and it was only obtained non-linearly. So it's kind of strange here. All right. So to conclude on that, we can say that it is a ratio of density differences, different density jumps, which select the most unstable wave mode. And there is a good agreement for the period or the frequency. And in fact, the symmetric mode was only obtained numerically as nonlinear feature. But we can also compare with 10 different liquid metal batteries that were used by in literature. So you have a list of these 10 possible liquid metal battery with a fixed current. And what people what people and us we have computed was a critical magnetic field for a fixed current going through this very shallow liquid metal battery. So when the magnetic field, the perturbative magnetic field is greater than this value, you have instability, and if not, you don't have instability. The system is stable. So anyway, so depending on the liquid metal battery, we see that we'll have different motion. Here in this case, the two interfaces will be in phase, and for the magnesium antimony case, which corresponds to the lowest critical magnetic field, you will have only the top interface. In fact, it corresponds to an antisymmetric mode, but in fact, only the top interface move. And so, but the conclusion of that is that the magnetic field is quite small because it is between 0.1 millitesla, which is about the Earth's magnetic field, till 1.2 millitesla. So it's quite small to get this instability. So this instability can be very dangerous. All right. And if we look at the current density, in fact, which is possible in these different liquid metal battery, in fact, what we see is that if you build some cylindrical liquid metal battery, it will be unstable. It will be unstable for a radius greater than 0.5 meters. So the other way around, liquid metal batteries with a radius which is smaller than 0.5 meters, so 50 centimeters, they will be likely stable. And people, in fact, people who manufacture this kind of battery, they use small battery, in fact. So they should be okay, they should be safe. So to conclude, we perform some theoretical calculation in cylindrical geometry with 2 or 3 layers. We validate this theory with computation, and we propose some experiments. But now I will continue with what is called electrovortex flow. So it is not an instability, because you can get it quite easily. It is a simple configuration, and the only thing that you need, in fact, is that if you have a small current collector, so here the radius of the wire is smaller than the radius of the cells. And you don't need external magnetic field. You can have, but first let's look at the case with no external magnetic field. So the mechanism was explained by Shercliffe. In fact, it is schematically represented here. So you have a current which is going into a liquid bath here. And so you have a localized current, which is mainly vertical. So I call it JZ. So this JZ, due to the rule of thumb, will create an azimuthal magnetic field in blue here. And because you have a liquid bath, in fact, the current will not only go up, but also on the side, let's say, so radially. So it will diverge radially. And now, if you think about the Lorentz force, you have the G radial with the B theta, which will give you a force. And this force, in fact, it is a rotational force which cannot be compensated by a gradient of pressure. And so that will create, in fact, a jet upward away from the collector. And this flow will be mainly in a poloidal, what we call a poloidal motion, mainly with radial component and vertical component like that. All right. And so people studied that in the liquid metal battery context, starting with Kelly and Sadoway in 2014. And so before 2018, we wanted to evolve through circuits. So I will present some studies some studies about the intensity of the flow. And so we start with this three-layer here, three-layer system. And so we have the two liquid metals. In between, you have the electrolyte, which is also salt. And so I will perform mainly axisymmetric computations. And to show that, I will just focus on what happens in a meridian plane. So I have small wire. The system is symmetric for the wire. And you have the three different fluids. Okay, so I will be showing some meridian view. And I'm choosing the magnesium antimony liquid metal battery with such physical quantities here. So what we have shown is that if the current is greater than 100 amps, the regime is inertial, meaning that the maximum velocity will scale linearly with the current density and inversely like the square with the square root of the density of the fluid. Therefore, because ρ1 is smaller than ρ3, we expect a stronger flow in the fluid 1, so in the top electrodes. Okay, let's look if it is true. So what I'm showing here is some numerical result only in the meridian plane. So here I have the radius, here I have the vertical axis, and I'm showing only axisymmetric computation, which are dominant, in fact. So let's look for this parameter here at the beginning and then at large time. Okay, what I'm showing here is the amplitude of the velocity field, and here the difference of the density, and here in between that correspond this white line correspond to the interfaces, the bottom interfaces and the top interfaces. And so here, just here, it is not the t equals 0, just above t equals 0. And so we see that the velocity is large along the vertical axis, meaning in fact that the flow will go this way. So it is away from the small wire. And so the small wire is at the top. And so the flow is going down here, and here is going up. And we see that it is stronger in the top layer as expected. So let's look now. What we see is that we have this poloidal motion, and we see that we have a vortex here at the top, a toroidal vortex at the top, which is stronger than the toroidal vortex at the bottom. And we see that, in fact, the deformation is more pronounced for the top interface. And in the asymptotic regime, we see that we have more and more small scales here, but we see that we have a variation here, but no pinch between these two interfaces. So what we ask ourselves is, can we have an estimate for the risk of pinch? Yes, we can, because you can think about you will have a pinch if you have enough kinetic energy in the light metal to reach the heavy metals through the thin salt layer, meaning that the kinetic energy needs to be greater than the potential energy due to the gravity. And delta rho is the difference between the rho electrolyte minus the rho top metal. So based only on this kind of a nice discussion here. So what we can say is that the maximum deviation of the interface will be given by the ratio between the kinetic energy divided by the potential energy. And so using the scaling of the velocity that we could get in the previous slide, we can have the estimate of this maximum deviation with respect to the current density. And that tells us that the maximum deviation will vary like J squared. And so what I'm plotting here is that the result that we got for different scenario. Imagine that you have 3 different current density going through this kind of battery, and you use similar battery. You use a similitude argument. And so we see that as expected, the maximum velocity vary linearly with the current density, but the maximum deviation vary as a g squared, so a parabola here. And so now, usually the electrolyte is in between 1 millimeter. Here is a deviation, maximum deviation in millimeter. So the electrolyte layer vary between 1 millimeter and 5 millimeters. And so we see that for this current density of 10,000 ampere per meter squared, we can have a risk and pinch for a radius between 5 centimeter or 15 centimeter. So the electrovortex flow will be dangerous in this case for quite fairly small cells if we have this kind of current density, and so if the radius is between 5 and 15 centimeter, you can get pinch. So you can get short circuit, sorry. And so, for example, I'm showing here a short circuit case for which I increase, in fact, the current. And so you see that you have the top interface will touch the bottom interface, and so you will have short circuit. Right, but now we have some scaling laws about the velocity, but we need to think that a liquid metal battery, in fact, correspond to mass transfer due to the fact that you have an ion of lithium, for example, we go from the top to the bottom layer. And so if you have a large current density, meaning that you have a lot of lithium ion going from the top through the salt into the bottom, you will have here a buoyant layer of lithium because the lithium is less dense than the lead. So therefore, you will have a buoyant layer which is rich with lithium ion. So now we will focus on the mass transfer corresponding to this battery, okay? And so for that, we need to model, in fact, the mass transfer, and we will use a mass concentration equation with a diffusion coefficient here. And I will use, in fact, molar fraction because people from electrochemistry use molar fraction. So I will represent molar fraction of lithium in the bottom layer. So I will focus in the bottom layer because it is here that we have the alloy that is formed in this liquid metal battery. And for that, to represent that, I will use a buoyancy term, which will correspond to Boussinesq term, which is given by this term here. All right? So let's look at what happens during discharge. So during discharge, the lithium ion is going from the top layer through the salt into the bottom layer. And I'm showing only the bottom layer here. And I'm showing as in color the molar fraction of lithium. And here I'm showing the streamlines of the flow. And so because we have a small wire here, we know that we have an electrovortex flow. But you see that during time, the electrovortex flow, in fact, is just killed because you have a lighter alloy on the top, which just act like a cork. And in order to measure the homogeneity of the alloy, what I'm plotting here is the difference between the maximum and the minimum of the molar fraction. So if this guy is small, that means that your alloy is homogeneous. And if it's large, it is not homogeneous. And so we see that with buoyancy, in fact, the difference is very large, and so we don't have any mixing because the electrovortex flow is just scratched due to the stratification. What happens in the opposite case, meaning in the charge? So in the charge, the lithium ion will go out from the alloy through the salt till the top layer, and I'm only showing the bottom layer. So now you still have the electrovortex flow, but because you are taking away the lithium, which is less dense than the lead, therefore you get an heavier alloy on top, And you see that this heavier alloy will just fall down and will form some plumes in the bottom electrode, in the bottom alloy. And so you get solutal convection. And this solutal convection is much more efficient than the electrovortex flow, and that will create some very efficient mixing. And so now, if I'm plotting here as a function of time, the inhomogeneity, we see that when we have diffusion, meaning that no flow, we have this solution. But if we have this solutal convection, we see that we have mixing of the alloy. And so I've performed also 3D computation. And in fact, of course, it is 3D, but we have exactly the same kind of order of magnitude for the mixing. But in this case, so for this electrovortex flow, which is only creating a colloidal flow, meaning a meridional flow, we see that it is not at all efficient. During discharge, it is not able to mix the alloy because the solutal buoyancy blocks the dynamic. And during charge, in fact, the buoyancy creates solutal convection, which is much more efficient than the electrovortex flow. All right, so now we were thinking of how to generate a sufficiently strong source of motion to enhance mixing in the discharge phase, because we don't want that. We want to have an homogeneous alloy. So what we add, we only add a vertical magnetic field. So now let us always focus at the bottom layer, only in the discharge, because it is when we want to have a mixing. All right, so now you have still the deviation of the current due to the fact that your wire is smaller than your battery. You have, and now you add a vertical magnetic field. And so the Lorentz force will be therefore GR cross BZ, which will just create an azimuthal force now, which like a blender. And so now, in fact, we will have an azimuthal flow, which is much more efficient. And so here, for example, before we add, we should get an electrovortex flow, which is mainly colloidal. And now what we get is that I'm showing the amplitude of the velocity. And so, in fact, you see that the flow is going the other way around. So we have this colloidal motion, but also this azimuthal motion, which is quite strong. And so what we perform first is an asymmetry study. So I remind you, for Bz equals 0 in discharge, we don't have any mixing. But now let's look when we impose some charge, and let's look at the repartition of the molar fraction. So I'm showing here a slice with the z axis in the middle. And so you see, if I increase the magnetic field which is imposed, we see that the mixing will be more and more efficient. We don't have the diffusive solution as before. And so we see here, I'm measuring the inhomogeneity with respect to time, and we see that the mixing is quite efficient as soon as the magnetic field is above 2.5 millitesla. All right. And so what happens in this case in 3D? Here I'm plotting the molar fraction in this bottom layer. And so the lithium is coming from the top. So that's why the molar fraction is higher at the top, but it is increasing during time. And so we see, in fact, at the beginning, the repartition will be axis symmetric, but at the end, it will be 3D. So just maybe to see it more easily, I will look on from the top. And so I'm still plotting the molar fraction of lithium. And so you see at the beginning that you have patterns which are axis symmetric, but after a while, you will have some spirals which will appear and which will make some 3D motions, in fact. And this kind of simulation, I could perform very few, because if you look at the numbers, so we see that the Reynolds number is still about the same order of magnitude of 14,000. But what is very difficult is the Peclet number, which corresponds to the characteristic velocity, the radius, divided by the diffusion term due to the density of lithium inside the alloy. And so you see that it is above 2 × 10⁵. So you need very small time step and a lot of very thin, very fine mesh. All right. And if you look at the velocity, because we want to have some scaling about the velocity, we see that the velocity is 3D and with a lot of small scales, mainly near where the blender is acting here with this azimuthal force. All right. And so the scaling laws is shown here. So the velocity, the velocity which is average in all the cell as a function of this parameter, and you see that you have a nice scaling law over 3 decades. So we can say that it is quite okay. And so we can say that the velocity, the order of magnitude of the velocity is given by that. I will use this scaling law to answer the question of how intense a fluid flow should be to be able to counteract the stabilizing buoyancy. And so now I will show some scheme. So here I'm representing, in fact, the layer which diffuse with this diffusion parameter during a time t, and so it will the thickness will grow with this kind of law. And if the velocity below is weak, the fluid won't be able to pierce this layer of less dense lithium ion. If it is moderate, it will be better. And if it's strong, therefore you will have mixing. And so if I'm looking to the velocity, to the order of magnitude of the velocity, we could find some scaling for the piercing flow, meaning that it is a minimum flow that to pierce through the stratified layer on an advective time. So if you take a fluid particle and you want it to go through this stratified layer, you find this velocity where beta is the solitary expansion coefficient and F is the Faraday constant, which is the total charge of mole. And M is the molar mass of lithium. And after, if you really want to have mixing, in fact, you need to consider that the fluid parcel will go all around the alloy during the same advective time. So it will be it will have enough kinetic energy to go all around. Okay, so that gives you another minimal flow. And now what I'm using is the DNS and saying that for this fixed current of discharge, I've seen that I have mixing as soon as the vertical magnetic field is greater than 2.5 millitesla, and before I have no mixing. So I'm plotting here the maximum velocity as a function of this parameter for the scaling law. And I'm using this feed, these three points which correspond to mixing. I can get the prefactor here, which depend on the setup geometry. And then I can now compare with the two criteria that I had. And so the U piercing in this case is here. So I see that the velocity that I get is greater than this U piercing. But if I'm plotting here the U mixing, the UM criterion, I see that it is only for these 3 points that the velocity is greater than this mixing criterion. And so therefore we can say that the mixing criterion is quite effective. And then we can use this mixing using the aspect ratio to translate this criterion with respect to the magnetic field. And so we found that if the magnetic field is smaller than this limit, this magnetic field won't have any influence on the mixing. But if the magnetic field is greater than this limit, we will have mixing which will be efficient. And if we use the numbers, we find that BZ need to be greater than 1 millitesla, which is consistent with our results. And so the take-home message for the swirling electrovortex flow, swirling means azimuthal flow. So it is efficient during discharge to enhance mixing as soon as the flow intensity is greater than with our criteria. And we found that the 3D simulations are very challenging. And so to conclude my talk, I have shown you that we can have different sources of motion due to the fact that we have electrical currents and induced or imposed magnetic fields, and also because of compositional gradients for which we have solitary convection. We have studied other instability. which is called stellar instability. What we would like to study maybe is thermal gradients, influence of the thermal gradients, but also the fact that in fact, a battery correspond to a difference of electrical potential, and we need to have other model for that. And so, in fact, in 2010, a startup company was created. Its name was Liquid Metal Battery Corporation, with Donald Sadoway, the professor from MIT, with different funding. And it was renamed Ambri. And so now Ambri, last year, in fact, they are selling large liquid metal batteries of 1 megawatt-hour capacity. And in fact, what they have chosen is here I'm showing one container with trays. The trays have a lot of cells, and this cell is what Professor Sadoway has in his hand here. So to conclude, I would like to acknowledge my colleagues, the project NC, for which I have CPU errors and Jean-Luc for computer, and I thank you for your attention.
So thank you very much, Caroline, for the very interesting talk. I would say we can open the stage for discussion if you agree. So whoever would like to ask a question, then just feel free to unmute your mic and ask the question, or you can write in the chat and I can report it. Well, maybe I can start then. Then it's about I have a question regarding the last slide you showed when you talked about the perspectives. Actually, when you say investigating thermal gradients, basically it would be the same kind of mechanism you showed at the end, but not just produced by the concentration of the ions, but it's more about really Bénard instability that's tending to promote mixing, right?
Yeah, in fact, if you look at the thermal problem here, as I said, here you have a salt, an electrolyte, which is for which the conductivity is less by a factor of 10 to the 4 less than the liquid metal. And so due to the Joule effect, you have G squared divided by sigma, the conductivity. You have a lot of heating here. So you have an internal heating, right? And so therefore, you will have a temperature which will be large here, and a temperature here, which can be small, but we don't really know that. But imagine that you fix the temperature at the top and the bottom at the same. And here you have a source of heat. And so therefore you will have Rayleigh-Bénard convection here because the stratification can be unstable, but you will have here a stable stratification in terms of temperature.
Yes. So
you can get Rayleigh-Bénard on the top, but stable stratification at the bottom. But the thing is that it is people have conducted such study, but the problem is that, as I've shown you here, you will have a lot of different, such cells, all in this kind of a container, and so therefore this heat need to go to eat the other cells also, and so it's not so sure. I'm not sure that you can consider that you have directly boundary condition at the top and the bottom. I'm not sure of that. I mean. So yeah, so I think that people were very interested academically on this kind of things, but we need to think of what happens if we have a lot of this kind of battery built in series.
I see, and actually, I did have a question also regarding still related to this, but regarding to what happens at the interface, essentially, because I mean this sort of system assumes that the temperature is sort of depending only on Z, or at least that would be the temperature at the boundaries, right? But there will be a distribution. The flow is not gonna be like isothermal, right? So do you think that other sort of instabilities like Marangoni-like?
Yeah, they are Marangoni-like. Kölner and collaborators studied that. but they studied that with in fact interfaces which were static. Okay, they didn't study in fact the possibility that the interface can move. But in fact, if you look at the order of magnitude of the velocity that you can get in this kind of system, let's say for centimeter or meters, meter dimension, the velocity is very small, right? So I think it's a good model for considering that you have flat interfaces, but you can get Marangoni. And also there is something that we want to study is that maybe you can get also so it's the thermal Marangoni. You could get Marangoni due to the solutal, so solutal Marangoni, but we could get also electrocapillary phenomenon also. But because you have different charges, and so these charges can impact, in fact, the surface tension. So it's kind of, I think these kind of things are not really known because it's really difficult to measure something in this kind of system.
Sure, because at the end, basically, it's all about the gradients of surface tension are all about the free energy which you have at the interface. Either it comes from the electrical part or thermal gradients or
exactly
concentration.
So it's really difficult to be able to discriminate this kind of because you know that the interface can vary. But what will be the most dangerous variation, let's say?
Yeah, but that could open sort of an avenue for microgravity applications, because basically in that case you would not need gravity to mix. You may manage to mix by an instability at the interface, maybe.
Yeah, but you want to build these batteries. So you want to have
sure. Yes. That's very practical. Definitely, there is also that part. So, thank you. So let's see if there is someone else who would like to ask a question. Just Jean-Philippe, go ahead.
Yeah. So thank you, Caroline, for this very interesting talk. I had a question. So you said that of course this battery can be used only to be static, and now it exists. So what happened in case of earthquakes where you have a mixing, when you have motion actually of the battery? Has it been tested or?
You mean what happens if there is? What do you mean by motion?
If you move the battery actually, because it's supposed to be static actually. So and all your studies you have done was on the static frame of reference actually. But
yes, they are static. But I think that what they will do is that imagine that you buy this kind of containers, and these kind of containers after when you go to this, if I visit Ambray, do I? But you won't see it because I'm not showing all the face. Okay, if you go there, you will have this container and a lot of containers. So you have more and more. And so what they will do, I guess, they will bring all these containers on place where you have your wind farm and whatever. They bring them. They need to eat, but they don't really tell how they do that, right? Because they don't give you. They have a lot of patterns, but they don't tell us what are the difficulties that they face. What do they do exactly in this kind of what is exactly geometry inside? But I think that they will. First you have to eat them, and in fact, what they have changed, in fact, the geometry at the beginning. The Professor Sadoway in 2013, he was saying that he wanted to build a large battery, just like the Oleroux cells. That's why I was showing this kind of geometry. The first scenario that Professor Sadoway was saying was imagine that we can use this kind of cells that people have built already. And so we were all thinking that it was he was planning to build very large ones, okay, with the 3 layers. But after they change totally, and they change in this model of having more small batteries, but all in series. And what they do also is that in order to have less instability, and because it is very expensive, in fact, when I'm plotting things like that, you see that you have the minus and the plus, let's say, the minus and the plus here, maybe. Sorry. Okay, you have the minus electrode and the plus electrode, and here on the side, you need to have an insulating device, an insulating container, and they use ceramic, but the ceramic is really expensive. And so now they totally change the geometry. They won't do that. They don't do that. In fact, what they do is that they add the bottom liquid and the molten salt, but here, instead of having the light metal in one layer, they put a foam. They use a foam which will have a smaller radius in order that it won't be in contact on the side with the other electrode. So the electrode plus will be from this side till the bottom, and then the minus electrode will be only a foam here. And so they only have to use a ceramic only here to isolate the minus and the plus. And so that changed totally the geometry. So now it will be more 2 liquid layers plus a foam. And I guess that they can have some problems also, because a foam will be a porous metal, which will keep the liquid A thanks to electrocapillary force. And you can get some drops, which can appear, things like that. So you can get all the instabilities, but they totally change the geometry from what they starting with.
Okay, thank you.
So thank you. Let's see if there are other questions. Just to the participants, just feel free to unmute your mic if you have a question, or you can write in the chat and I can report it. Okay, so maybe can I ask you another question?
Sure.
It's regarding the geometry of the battery which has been built, right? So the one you showed at the very end, that was in the hands of Professor, I forgot his name, from MIT.
By the way.
Yeah, I'm sorry. So is it like rectangular cross-sectioned to avoid the wave, or to perturb the instability, the wave kind of
instability, maybe.
Yeah.
Yeah.
Because I thought that basically the instability is like breaking the symmetry by the term of like the magnetohydrodynamic coupling term, because that's a curl. So basically you break the symmetry, and so there is not anymore the possibility to actually have a standing wave. And so in this case, you not only need to take care of rotating waves, and you basically break them by promoting by actually suppressing circular symmetries, right?
So that's true that in cylinder you always have the resonance between the waves. Yeah. But in a rectangular cells that people studied a lot, because it is exactly the geometry of the Hall-Héroult cells for the aluminum reduction cells. But you can get, in this case, you can get a resonance between the let's say the wave along X and the wave along Y. And so what people have studied is how to control this kind of instability in order not to get it. Because we know that the way to do it, in fact, is to have a large thickness for the electrolytes. But the electrolyte, the cryolite and alumina, if you take a large thickness of these kind of things, you will have the Joule effect So you will spend G squared divided by sigma. So you will spend all your energy in Joule effect. And people just found that it costs 3% of the total energy cost of the world in the aluminum reduction cell, just to manufacture aluminum. So the idea was to get the thinnest layer of cryolite, but without short circuit, because as soon as you have a short circuit, you need to stop all the production, and you need to take out the cathode, and because the cathode will be destroyed, and you need to take out the cathode to replace it and to put down again. And so that's why people just wanted to control this metal parallel instability in Olero cells. And that's why they use a lot of different possibility for that. Bojarevich is a main specialist on this kind of things.
Okay.
Mm-hmm.
Okay. Thank you. That's that's very interesting. Thanks. So last call. Is there someone else who would like to ask a question, or just Jean-Philippe, go ahead.
I may have a last one, very general. I think that if I remember, you said that the number of cycles that you can do with this kind of battery are a bit higher actually. But do you know what is the limit? What limits the number of cycles actually in this kind of battery?
We should ask two electrochemists.
Okay, it's not anymore the same mechanism than the other battery actually.
No, it's not at all the same mechanism, because in this case you have really you have interfaces which are liquid and not solid. So in the solid you can get some cracks, and that's why that is the main limitation, is that you have cracks between fissure. I don't know say that, cracks on the solid part of the electrodes. But here it is all liquid, so the interface we just won't have these kind of things. But they say that it is 10,000 maximum of a cycle. So I know that you can get this kind of intermetallic phase. I mean, if you don't mix enough the alloy at the bottom, you will have the formation of metals, and these metals, that they call it intermetallics, and this metal we just in fact make kind of small short circuit. It will reduce in fact the difference of potential that you want in your battery. Okay, but it is reversible. I mean, as soon as you mix more, it's okay. You recover your difference of potential. But I don't know exactly what limit. I know that it is much more. I mean, you have much more cycle, but it can be this intermetallics. I know that you can have some dendrites also, but it's more in the electrochemistry problem. Yeah.
And maybe a very last one. You said that you need to. It has to be at high temperature, so it use some energy, I suppose, to do this. So do we know that if it is efficient actually? If we don't spend too much energy in order to maintain some energy? Actually?
No, because I think that you have in fact, if they do it well, I guess they do it well. I mean, as I said here, once you have your liquid, you have melt all your liquids. So you need, you pay for that. But once all this system is working, you have a thermal resistance in the middle, which is electrolyte, because you have the current J squared divided by sigma. Sigma is very small, and so J squared over sigma is an intense source of energy.
Okay.
So I think that they can use it. I guess they need to optimize their different cells that they put in series, such that as soon as they are all melt, they use the Joule effect in order to stay liquid.
Okay. It just needs to be insulated from the exterior, let's say, of the battery, but to maintain the heat. But
no, I think that it will be easy. I don't know. I don't know exactly. They don't tell. They don't
of course.
on the website. But because of that, you have this thermal resistance, and you have. I think that you pay at the beginning, but after it should be able to stay hot by itself. If you isolate if you put all your small batteries in series and you isolate that, you have a source, an internal source of heat.
Okay. Okay. Thank you very much.
Okay.
So yeah, that's funny because I attend a seminar for which somebody was talking about all solid battery. So you have the all liquid battery, and now you have the all solid battery because they could manage to make an electrolyte which is solid. So you have the two technologies now.
Okay.
That's interesting that there is so much development on this specific area because there is demand apparently for what you said at the beginning. Yes. It is, yeah. We need to use all the things that lithium, because the resources in lithium is finite, and we need to use something else. Yeah, no, definitely. Okay. So thank you very much, Caroline, for this very interesting seminar. And as you could see, it's kind of triggered a number of questions. So thanks again, and I invite our participants to thank the speaker once again. And thanks again for having accepted the invitation. Thank you. So have a good evening to everyone. And thank you once again, Caroline. Bye-bye. Bye.
Thank you, Caroline.
Bye.
Bye.